thank you very much. What I'm talking about today is joint work with Matthew Kwan. I mention that again later. Okay, so let's start. Let's start very slowly. So assume you're given a polynomial p in n variables, x1 to xn, let's say with real coefficients. How many solutions does it have? Well, of course, that doesn't really make sense because normally it's infinitely many. Okay, so let's ask a better question. So questions that some people ask in analytic number theory is, how many solutions does it have in a box of the form, I mean, the integers from minus b to the n, so that's some bounded box. I mean, we can count the number of solutions, that all makes sense. And so in analytic number theory, typically people ask this question when the polynomial and therefore n is fixed and then b is taken to be very large, and then they investigate this. And this is very interesting, but that's not the topic of today's talk. So today we sort of ask the opposite question: what happens if we take b very small? So maybe, I mean, taking b to be 0 doesn't really make sense. So if we could maybe make our box as small as possible. Let's say it has 2 points. So now we could take the 2 points to be 0, 1. Then up to variable transformation, it's the same as taking the -1 or 1. So let's stick with that because that's sort of the more common settings, okay? So we asked the same questions here, this analytic number theory question that's intensively studied, but we now only care about solutions in -1, 1 to the n. So we care about solutions where every variable takes value -1 or 1. And so now we sort of do the opposite. We imagine n to be very large. So we fix sort of this very small box, this hypercube, and we take n to be very large, and then the question is, given such a polynomial and n variables, how can we bound the number of solutions on these hypercube vertices -1, 1 to the n? And so that question is typically not studied in number theory, but instead in probability theory. So such questions are studied under the name of polynomial anti-concentration inequalities in discrete probability theory. And just because most of you probably don't come from the probability theory side, let me give a little bit of context to this. So in probability theory, what's much more prominent than anti-concentration inequalities is actually the opposite, namely concentration inequalities. So concentration inequalities play a central role throughout sort of almost all of probability theory, and such concentration inequalities state that certain types of random variables are likely to lie in a small interval around the expectation. So they're typically close to the expectation and don't deviate too much. So that's what concentration is about. But anti-concentration is sort of the opposite phenomenon. So anti-concentration talks about that a random variable is unlikely to fall into a very small interval, or at the most extreme is unlikely to take any particular value. So in anti-concentration, we want to study sort of statements of the type that a random variable is not too likely to take any particular value. And so that's not in contradiction with concentration, because concentration says, okay, typically I'm somewhere in this interval, but then anti-concentration says, well, any particular point in this interval I'm still not so likely to take. Okay, so that's what anti-concentration is about. And sort of the most classical result in the spirit is the so-called Littlewood Offord theorem, which is written here. And so that's sort of exactly the question we had on the previous slide for linear polynomials. So the Littlewood Offord theorem from 1945 states that if we consider a linear polynomial with non-zero real coefficients, and now we take independent, unbiased random variables in 1, -1, then the probability that this polynomial takes any particular value z is at most a constant times 1 over square root n. And so that's exactly what we talked about on the previous slide, because that basically says if we care about the number of solutions in 1 -1 to the n, then it's at most a 1 over square root n fraction of those sort of points, of those hypercube vertices, which can be a solution to this linear polynomial. Okay, so here's again the statement. And so just to sort of see that we can really look at the statement from different perspectives, so a more geometric perspective on the statement is that for any hyperplane given by, so for any FR hyperplane which is then given by such an equation, under the assumption that the coefficients in this equation are non-zero, the number of vertices of the hypercube which lie on the hyperplane is at most this. So it's at most a constant over square root n fraction of all hypercube vertices. And then again, we can also phrase it in the language of what we of the question we had on the first slide. So if given such a linear polynomial with these conditions here, so again these conditions, the number of solutions is at most this. And so let me point out that for the analytic number theory question I raised, as far as I understand, the linear case is considered trivial, whereas here, even this linear statement is actually non-trivial. So that's a non-trivial statement. First, Littlewood and Offord investigated this and proved a weaker bound of the form a constant times log n over square root n. Already in that, you see that's a non-trivial statement because some serious people first proved a weaker bound, and then Erdős sharpened the bound to what is written here. Okay, so here is again the theorem, and let me also remark that this bound is tight. So for example, you can take all coefficients to be 1, and then you can see that this is basically looking at how big is the middle binomial coefficient compared to 2 to the n, and then you find that this bound is it's tied up to this implicit constant factor here. And the theorem can be proved combinatorially using Sperner's theorem on antichains in the Boolean lattice. I guess probably some of you have seen this proof, but also for time reasons, let me not go into this. So let me just say that it's a combinatorial proof talking about antichains, so subsets of some families of subsets of some ground sets where none contains the other, and then in that setting you get a bound, and then you apply this here. So that's how Erdős proved this. Okay, so let me also, so maybe for those of you who have never seen this, this may sound like a strange question, which sort of is a little bit unclear why anyone would study this, but in fact this is a very important theorem. So this theorem and various of its variants and strengthenings in various directions have many applications, for example, in random matrix theory, in combinatorics, and in theoretical computer science. So this is really actually an important statement. Okay, but so in the linear world, I think this this was proved in 1945, and also generally the situation under various additional conditions on the coefficients is rather well understood, what bound you can get here in terms of the conditions you put on the coefficients. That's all rather well understood in the linear setting. So maybe the next question is, what happens when we consider polynomial of higher degree instead of a linear polynomial? So let's remember that in the first slide we also started with an arbitrary polynomial, so it's very natural to also ask what happens here if we take a polynomial of higher degree. And so then we arrive at what's called the polynomial Littlewood Offord problem. So there the setting is we have a bounded degree polynomial with real coefficients, so we start with some sort of degree bound. So let's, in the previous slide we had linear, now we could consider, let's say, quadratic or degree 3 or whatever. You fix your degree, then you consider n to be large. And you take a polynomial with real coefficients, you again take independent unbiased random variables and 1 minus 1. And the question is again, what bounds can we give for this? So how large can the probability be that the polynomial takes any particular value if we plug in 1 minus 1 randomly for the variables? Okay, but in order to have any hope to obtain any meaningful bounds there, one needs some assumptions on the polynomial. So clearly, if it's a constant polynomial, then this is very boring because the probability can be 1. So that we need to sort of exclude. So let's remember that in the linear case, we assume that these coefficients are non-zero. So in other words, we assume that each of these xi's actually appears in the polynomial, because in the linear case, if the coefficient is 0, that's the same as actually not using that variable. So maybe it would be natural to put as our condition that all the variables should actually appear somewhere in the polynomial. But actually, even that is too weak. So for higher degree polynomials, even if we assume that every variable actually appears in the polynomial, meaning that it appears in some monomial with a non-zero coefficient, that's not enough to get a reasonably good bound. So here's an example for this. So for example, if you take your polynomial to be this one, then the probability that this takes value 0 is at least as big as the probability that this first factor takes value 0. But that happens with probability 1/2, namely exactly if the first and the second variable have opposite signs of each other. And 1/2 is not a very good or interesting bound. So we want a bound which is kind of good with respect to n. So that assumption clearly wasn't good enough. We need to think harder about a better assumption. So, but we can sort of, if we think about this more, we'll discover that more general, if it is possible to fix just a small number of these variables to certain values in such a way that then that completely determines the outcome, like depending on the structure of the polynomial, that may be possible, that if I fix some of them to certain values here, then sort of all coefficients of the remaining variables sort of cancel out and the polynomial is completely, the value of the polynomial is completely determined, then that will automatically lead to a rather large point probability of this, right? Because we just need those to take those particular values here. So that would be a bad setting for us, so that we sort of need to exclude. So that means we need to assume that one cannot fix a small number of those variables to certain values in such a way that then the value of the polynomial is determined. So that's sort of the assumption we need. Okay, so that's a little bit of a complicated assumption if you just want to think about the structure of the polynomial. So it's a natural assumption for this problem. But if we want to sort of think about assumptions which talk most directly about the structure of the polynomial, we can get certain sufficient conditions which imply this. So for example, it suffices to assume that this polynomial has a lot of non-zero coefficients, meaning linearly many. So in total, if it is a degree d polynomial, then this can sort of, in theory, has up on the order of n to the d coefficients. And if we impose the condition that linearly many of them is non-zero, are non-zero, then this will in particular imply that type of condition. So that's a natural condition that one can work with and that researchers have worked with on this problem in the past. An alternative condition is the following, which is a bit weaker than that one. So this alternative condition is if the degree of the polynomial in D, then it also suffices to assume that this polynomial has linearly in n many multilinear degree d monomials with non-zero coefficients involving pairwise disjoint sets of variables. This sounds more complicated, but actually, so what it says is just you have various multilinear degree d terms, each appearing with non-zero coefficients, and so that the variables are disjoint. So basically, you have a bunch of sort of groups of d variables which occur together, their product with a non-zero coefficients, and you sort of have linearly many in n disjoint such sort of sets of d variables each. And so so this condition implies that, but that one is strictly weaker. And that condition also suffices to for that type of thing. So as you can see, there's various reasonably natural conditions you can put on the polynomial, and different researchers who've worked on this problem have worked with different types of those conditions. Okay, so here is sort of for general degree D, so fixed degree D, but sort of general D, the best result that is known on this. So that was proved by Nguyen and Vu roughly 10 years ago using a result of Kwan and Boolean analysis. So what they proved is that if you have a polynomial of fixed degree D with real coefficients, now with this sort of assumption at the bottom of the last slide, so with this assumption that you have linearly in n many groups of d variables appearing with non-zero coefficients which are disjoint. So don't worry too much about the technical assumption, but with one of the assumptions on the previous slide, namely the bottom one, then what they proved is if we take xi1 to xi(n) to be independent random in 1 minus 1 to the n, then each in 1 minus 1, then the probability that this polynomial takes value exactly z is of this form. So remember that the sort of previously the bound was sort of 1 over square root n for the linear case, and here they have this additional logarithmic term in the numerator. It is conjectured, though, that this bound, that the logarithmic term here is not necessary, so it's conjectured that actually the bound should be again on the order of 1 over square root n. So that would be exactly the analog of the Erdős-Littlewood Offord theorem for linear polynomials in the higher degree setting.
Does the implied constant depend on the constant in the omega n?
Yes, so that implied constant should depend on this constant and on the d, right? Because so that the degree is considered fixed, so that will in fact affect the implied constant and also this constant here. Okay, So here's again the conjecture that sort of in this setting you have a polynomial of some fixed degree d, you take n to be large, you have this reasonable non-degeneracy condition that we convince ourselves we need something of that form. I mean something roughly of that form, so we need some type of condition, and here is one. Then the statement is that if we take the variables to be randomly in 1 minus 1, then the probability to take any particular value z is at most of the form constant over square root n. That's the conjecture. And so if this is true, the bound here would be tight. So one could wonder whether sort of if the degree is higher, couldn't I maybe even hope for something better than 1 over square root n? But in fact not. For example, if you take the polynomial to be just the sum of the variables and then to the dth power, then clearly, or alternatively, if you don't like that polynomial, you can also take any other polynomial divisible by x1 plus and so on plus xd, and the probability to take value 0 is at least the probability that this takes value 0, and that we already convinced ourselves has to do with the middle binomial coefficient and is on the order of 1 over square root n. Okay, so the conjecture, if it holds, is tight, and we also know that it holds in the case d equals 1 because that's the Littlewood Offord theorem for linear polynomials. Okay, but in general, as we also saw, the best known, in general, the conjecture is not known, and in general, the best known upper bound is roughly of this form, but with an additional power of log n in the numerator. Okay, so this talk is actually focused on the quadratic case of the conjecture in the previous slide, so on the case d equals 2. So then we arrive at the so-called quadratic Littlewood Offord problem, and just to state the problem again, I call the polynomial Q now because that stands for quadratic. So we have a quadratic polynomial with real coefficients, which, let's say, just for simplicity, we take the sort of easiest of those conditions, so that it has many non-zero coefficients, meaning linearly in n squared many. Then we can ask for independent, unbiased random variables, what bounds can we give for this probability? And of course, you can also take the other notions of many non-zero coefficients that we had on the previous slide, like with this disjoint sets of variables and so on. Okay, so that's the natural degree 2 generalization of the classical Littlewood Offord problem for linear polynomials, which, as we discussed, was resolved by Erdős in 1945. But sort of now, sort of for the quadratic case, despite this has been a long time ago, and despite there was actually despite a lot of research specifically on the quadratic case, sort of until recently there was not much progress beyond the general bound of Nguyen, and Vu. So, and maybe let me also mention that this quadratic version was in particular popularized by Costello, Tao, and Vu in their study of discrete random symmetric matrices and their singularity probability. So if you want, so in discrete random matrix theory, sort of studying the singularity probability is a central theme, and if you consider symmetric matrices, then when you study sort of, well, what's the probability of various minus sort of having zero determinant, you very naturally arrive at the quadratic Littlewood Offord problem. And so that's why sort of they worked on it, and they also popularized it, and then more people worked on it. Okay, so here's again the problem, and as we just said, there are many different ways how we can make this assumption of having many non-zero coefficients precise. So, for example, we can talk about having linearly in n many of these multilinear degree 2 monomials with non-zero coefficients with this pairwise disjoint sets of variables, but there's also this version of having n squared many non-zero coefficients. Okay, but so under various such assumptions, so the different works listed here use different assumptions, but let me maybe not go into detail which work was exactly under which assumption. So under various different such assumptions, the following upper bounds for this problem were proved. So first, Costello, Tao, and Vu proved sort of when they originally started looking at this problem in the context of these discrete random matrix theory problems, they proved a bound of a constant times 1 over n to the 1/8. So that's still sort of, I guess, polynomial shape, but it's sort of, I guess, in some sense quite a bit away from the 1 over square root n that one would expect. And the same bound actually also follows from work of Rosinski and Samorodnitsky from 1996, but I think that was unknown to them at the time, and that only sort of, there were different communities and they weren't really aware of each other. Okay, so then Costello and Vu improved this bound to n over, constant times n over n to the 1/4. So that means the exponent here was improved from 1/8 to 1/4. Then a bit later, Costello proved an exponent which was almost a half. So he proved 1 over n to the half minus epsilon for any fixed positive epsilon. And then Nguyen and Vu proved this result, which was more general for any degree d, that we already saw on one of the previous slides with this logarithmic term in the numerator. So that is in some sense already pretty close at the conjecture of 1 over square root n, but still not quite there because we still have this logarithmic term here. And so what I want to talk about today is joint work with Matthew Kwan, in which we finally resolved this problem, proving sort of the sharp bound on the order of 1 over square root n. So we proved that, okay, so this looks a bit technical because I sort of put the exact assumption, but don't worry too much about the assumption. But I go through it once, but now you can, afterwards you can forget about what was the exact sort of condition we put in the polynomial. Just remember that you had to put a condition, and you have a bit of flexibility which one to put. But so we sort of put the strongest one, so that's why I wanted to state in the strongest form here. Okay, so the statement is if you have a quadratic polynomial with real coefficients, with assumption that we cannot fix less than m of these variables to certain values in 1 minus 1 in such a way that it already completely determines the value of the polynomial. So that was sort of the first assumption we talked about, the one we really need, so this sort of the weakest of the possible assumptions we can make, therefore leading to the strongest statement. So we put this assumption that we can't fix few variables to determine the value of the polynomial, when we choose the remaining variables again in 1 minus 1. So that's sort of the weakest possible assumption you can put there. Then what we show, and that's more important than what the exact assumption is, then what we show is that if we again take psi 1 to psi n in minus 1, 1 independent uniformly random, then the probability to take any particular value z is at most of the form constant over square root m. Okay, so m here was the number of variables that we sort of, the number of variables that we would need to fix in order to determine the value of the polynomial. Okay, but so in particular, this assumption, as we already discussed earlier, automatically satisfied if we have m multilinear degree 2 monomials with non-zero coefficients with pairwise disjoint sets of variables. So if we have linearly many such monomials like in the assumptions of the previous works, then we get the bound of 1 over square root n that sort of we were hoping for. And so in that sense, our assumption here is weaker than the assumption in the previous works, and therefore sort of is a stronger result with this weaker assumption. Okay, but as I said, don't worry too much about the precise nature of the assumption here. Just wanted to once state the exact assumption we put. Okay, so here's again the statement. And so let me maybe briefly also mention that we also proved a generalization of this, where these are arbitrary independent discrete random variables rather than 1 minus 1 value. So the proof sort of transfers to that, or rather the result can be in some sense black box to transfer to that. But so I don't want to focus on that in this talk. So in this talk we stick with 1 minus 1. And so maybe also let me just briefly mention that as an application of this result, we also resolve a conjecture of Alon, Heffel, Skrivelevich, and Tyomkin concerning the so-called edge inducibility of graphs. So that's some sort of graph theory problem which asks about sort of how many k-subsets of vertices on a graph can have exactly L edges. And so that was a problem that Alon, Heffel, Skrivelevich, and Tyomkin asked in 2020, and in fact they sort of made 3 conjectures, and 2 of them were resolved the same year, and sort of the third was then resolved by our result here via a reduction to Kwan, Sudakov, and Tran, who resolved that conjecture up to logarithmic factors using this Nguyen and Vu result. But so if we now instead take our result, then we get the sharp conjecture of on this graph theory problem. But again, that's not the focus of today's talk. Okay, so for most of the rest of the talk, actually, how long should I talk exactly? 50 minutes or an hour, or what was, I forgot to ask you. Exactly an hour, so I shouldn't leave time for questions. Okay, great. Okay, so then, that's great, then we can go very slowly. Okay, so for most of the rest of this talk, I want to give you an overview of the proof of this result. Okay, so again, this will, I mean, the paper is rather long, and a lot of the technical details are quite complicated, and I swipe all of them under the rug today. I just want to explain the idea and the general strategy of the proof to you. Okay. So we are given this quadratic polynomial under these assumptions, which we'll also forget now because we'll forget all technical conditions here. So we're given this quadratic polynomial, and we consider independent, unbiased random variables in 1 minus 1, and we ask, so what's the probability that this, if we plug those variables in, can take any particular value z. And so like all of the previous papers on the quadratic Littlewood Offord problem, our proof uses a technique called decoupling. And so I want to briefly explain what that is. So first, we use a decoupling inequality, or where maybe our starting point is a decoupling inequality, which was observed by Costello and Vu. And so the idea is the following. So let's look at the index set of these variables, and let's just partition this into two subsets. So the indices 1 to n, so the n variables will be partitioned into two sets. I and j are the index sets of this partition. And so that means our random vector here, so we sort of put together these random variables in a vector, and so that vector will then be broken into these two parts, and these two subvectors are independent. So that's very important for us, that the vector with just the variables with indices in I, that's this one, and the vector with just the indices in j, that's this one. Those one are sort of truly independent of each other probabilistically. Okay, so now the trick is, let's take an independent random copy of this vector. Okay, so we sample this not just once, we sample it twice independently. Why is not quite yet clear, but you'll see in a moment. And so then we observe the following. The probability that our polynomial takes the value z, that's of course the same as the probability, we just sort of change the notation here, that the polynomial, if we evaluate at the I vector and the j vector, takes value z. So that's just a notation change from here to here, nothing happened. But now something happens. So the probability that this is z is at most the probability that this is z, and it's also z if we plug in the other copy of the I vector. So that both this happens, and it also happens for the psi prime I vector, so for this independent copy of psi I, that both of those happen simultaneously, and that probability to that 1/2. That's an upper bound from the probability that just the first thing happens. So why is that? There's different ways to see this. Sort of, some people prefer saying that's by the Cauchy-Schwarz inequality. Other people prefer saying that's because of the arithmetic quadratic mean inequality. I don't want to take a stance on this, but in either case, by some well-known, rather elementary inequality, one can check that this indeed holds, and I don't want to do the calculation out here, but you can probably believe me that if one sits down and calculates for 10 minutes on half a page at most, more like 2 or 3 lines, then one gets this. Okay? So just by sort of, say, the Cauchy-Schwarz inequality or arithmetic quadratic mean, we can bound the probability that we're interested in the square root of the probability that both of these things happen. So far it's unclear why we would want to do that, but now here comes sort of the main point why Costello and Vu did this. So they then sort of made the next observation, which is sort of trivial in itself, that the probability that both of those equations hold, so that both of these values are equal to z, is at most the probability that the difference of those two values is 0. So that's clearly true. And so that means this probability can be bounded by the probability that that difference is 0, and then with a half here. So now, why would you want to do that? Well, if you look at this and you fix, sort of, yes, you say you expose or condition on your outcome for xi, this vector xi I, and also for xi prime I, and you just look at this as a sort of in the randomness of this xi j, then this polynomial originally we started with a quadratic polynomial, but then this polynomial just in psi j after we fix the other variables is not a quadratic polynomial anymore, it's a linear polynomial. And the reason for that is that the terms which are quadratic in this psi j, they appear here and in the same way here, and so they cancel out. So if you look at this, this is now, at least after we sort of expose and condition on this and this becomes a linear anti-concentration problem, and linear problems we know how to study. And so that's the whole reason why we want to do that. Okay, so here's again a summary of sort of the setting we had, and now here what we just said is that Costello and Vu observed that if we take this partition, then we have this inequality. That was the one sort of with 3 steps on the previous slide. And so the point is now that for any given outcomes of psi I and psi prime I, we can interpret this here, this polynomial, as a linear polynomial in psi j because the quadratic terms cancel, and so that means we get a linear anti-concentration problem. And so that means we reduce the quadratic problem to a linear one, and so that means we can now get a bound by applying the Littlewood Offord theorem to this linear problem. So for typical outcomes of psi I and psi prime I, this resulting linear polynomial in psi j has many non-zero coefficients, so then we can apply the Littlewood Offord theorem. That in itself gives a bound of constant times 1 over square root n, but we have this additional half here in the exponent, which we shouldn't forget, and so therefore we get n to the 1/4. So that's how this 1/4 bound was proved by Costello and Vu. Okay, so here's again a summary. So with this decoupling technique, they showed this, but the problem is that by this decoupling, by this half exponent here, we incurred a square root loss. And just sort of doing it like that, you can never get a better bound than n over 1/4 because you get the square root loss. So now the question is, how can we get around the square root loss here? And so what we do is we use an iterative decoupling scheme. So we sort of decouple multiple times in such a way that it allows us to avoid the square root loss. So let me explain in a bit more detail what I mean by that. So in the first step of our decoupling, So in the first step, this decoupling inequality of Costello and Vu reduces the problem in the following way. So we started with this probability we care about, that the polynomial takes exactly value z. And then, if you remember on 2 slides ago, no, maybe 1 slide ago, I don't remember, so we had this term. So we looked at the probability. So here psi prime I was an independent random copy of psi I. And we looked at the probability that this comes out to z and this comes out to z simultaneously, and we had this half here. And this half came from Cauchy-Schwarz, or the arithmetic quadratic mean inequality, and so there's no way at this point to avoid the 1/2. But so now if you remember, the next step of Costello and Vu was just to take the difference here, so just to upper bound this by saying the difference is 0, and that step in some sense was really lossy, and we tried to get better at that step. So our idea is to sort of do this iteratively, and so maybe the other observation here is, that will become maybe more clear even on the next slide, but so here we have 2 quadratic equations, but sort of the main insight, or one of the main insights is to rather look at this like 2 quadratic equations. We can actually look at this as 1 linear and 1 quadratic equation, because we still have the linear equation from the difference and then 1 of the quadratic equations. I have that again written out on the next slide, but so this way we sort of interpret this as a problem with a quadratic and a linear part, and then we want to sort of iterate this idea at every step, reducing the proportion of the problem that is quadratic. So to get a more and more and more linear problem to in the end get sort of the tight bound. Okay, so in order to explain this better, however, it's helpful to take a more geometric perspective on this. So, and I think for many of you, this geometric perspective will actually be very natural, much more natural than for probabilists. So we are given a quadratic polynomial, and so now we are looking at its solution set, and so now, so the solution set of sort of the quadratic polynomial being equal to z. Alternatively, you can look at the 0 set after you subtract z from the polynomial. It doesn't matter. So you take that solution set for this equation, and that's now a quadratic variety. And that's the point of view that is helpful to take here. Okay, so now we are considering independent unbiased random variables, xi1 to xin and 1 minus 1 as before. And so now the probability that we care about is exactly the probability that this random vector lies on Z. So I think to all of you, this step will be, I think, very natural. Okay, so we can now rephrase this sort of decoupling idea in this language. So the probability we care about is the probability that the random vector lies on Z. And so that, I guess, by this decoupling, as we saw before, is at most the probability that this comes out to Z, and it also comes out to Z if we take psi I prime instead of psi I with the exponent of a half here. And so now this we want to now rewrite as the probability that the difference is 0. So that's exactly what Costello and Vu did. But in addition, we want to keep the first equation. So the probability that both of these things hold, that's just exactly the same event, that the difference is 0 and the first thing holds. Okay, and so now we didn't forget as much information, so that's good. So far that seems sort of trivial, that we do better when we don't forget the information. The problem is, of course, that now we still have a quadratic equation here, so we can't just apply the Littlewood Offord theorem and be done anymore, right? So, I mean, there was a reason why Costello and Vu sort of chose to forget this, namely that they can afterwards apply the Littlewood Offord theorem. Okay, but so we want to remember this, and now sort of keep going with our decoupling scheme. So, okay, so let's analyze what this means here. So again, if we fix psi I and psi prime I, so those you should consider as fixed, and now just look at this problem in psi j. So now psi j is the random thing, the random vector, and now let's look at the variety described by these two equations. So, so this thing here describes that psi j lies in the variety described by those two equations, and this first equation is, as we said, linear, because the quadratic terms in psi j cancel out, and the second equation is still quadratic in psi j. So that means we now have a probability that psi j lies on a new variety, and this new variety is given by one quadratic and one linear equation. Okay, so here's again the setting we had. We looked at this variety given by one quadratic equation. We took this partition, and now for any given outcomes of psi I and psi prime I, we were now interested in this new variety that was at the bottom of the previous slide, given by one linear equation here and one quadratic equation in this X. And so now what this decoupling said exactly on the previous slide is the probability we care about, which is the probability that the total psi vector lies in Z, is at most the probability that the psi j vector lies in this new variety given by this linear equation, this quadratic equation to the 1/2. So at this point, you might shake your head and wonder, well, what's the point of all of that? Like, I started with one quadratic equation, which is already hard enough, as I hopefully convinced you that this isn't a trivial problem for the quadratic equation. What I did is, I said, okay, decoupling, complicated inequality, well, not so complicated inequality, but decoupling. And then afterwards, I have a variety described by a linear and a quadratic equation. That seems strictly more complicated than just a quadratic equation. So what's the gain here? Well, the gain is, I guess, that our idea is to sort of make the problem more and more linear. And so the way we want to look at this now is that we have this variety which is described by this one linear and this one quadratic equation, but we can equivalently just say that this is a quadratic equation, so that's a variety described by the solution set of a quadratic equation on a linear codimension 1 subspace. So this variety here has in particular this linear equation, so it lives in a linear codimension 1 subspace, and on that linear codimension 1 subspace, I have an additional quadratic equation, and that describes my variety. So there is the variety. So again, I mean, that sounds strictly more complicated than just a quadratic variety by itself, but the idea is now to keep going with the scheme and sort of impose more and more, sort of reduce more and more the codimension of this linear subspace with the aim of sort of, I guess, heuristically making the problem more and more linear. Okay, so let's analyze how sort of what happens here. So if we take typical, so this variety we look at here, of course, depends on these outcomes of psi I and psi prime I. But for typical outcomes of them, we would expect that the probability of this lying on this we would very heuristically, like we can't prove this at this point, but we would very heuristically expect that the probability of this is only 1 over n and not 1 over square root n, because we have 2 equations to satisfy. And sort of very heuristically, one could naively hope they're roughly independent, so the probabilities should multiply, so we should get 1 over square root n times 1 over square root n. And so just reality check, if we get this and get 1 over n here, then with the square root together, we get 1 over square root n, so we are fine. So far, we didn't forget too much information. A reality check yields that if sort of things work out nicely, we actually did indeed avoid the square root loss. And so that's our goal, to keep going, sort of avoiding the square root loss, but still trying to maintain sort of, well, like if you imagine you keep going with this decoupling, I mean, it looks like it's going to get more complicated, but we need to, with this linear structure, somehow we are able to, I mean, we use this linear structure to sort of keep control over what's happening and sort of therefore avoid the square root losses until we can suddenly at some point afford them, but we'll get to that later. Okay, so here's again sort of our setting. So we had this variety, this one which depended on the outcomes of xi I and xi prime I, but just to make the notation less clumsy, I'll omit the subscripts here now. So this is a variety described by the solution set of a quadratic equation on a linear codimension 1 subspace, so on a hyperplane. And so for typical outcomes of those, our goal is now to bound the probability that xi j is in this. And to do that, we now want to apply decoupling again. So in order to do that, we now need to partition J again. So we partition J in a set I2 and a set J2, and we consider again an independent random copy of the I part. So xi prime I2 is an independent random copy of xi I2. And so now, if we decouple again, what happens is that the probability that this xi j lies in this variety up here is at most the probability that the j part sort of lies in it, both with respect to the xi I2 and the xi prime I2. That was exactly what we had before, and then with this additional a half. So that's exactly, again, Cauchy-Schwarz, or alternatively arithmetic quadratic mean, whichever way you prefer. So again, sort of this probability can be bounded by the probability that it works between I2 and J2 and I2, and simultaneously between J2 and xi prime I2, and then with a half here. And so now, just to explain this notation, it's maybe sort of suggestive, but this variety here denotes the sets of all the possible sort of vectors in R index with entries in R indexed by J2, where this lies in the Z1 thing, and analogously for that. So, I mean, just to explain this notation, but it's sort of what you think it is. Okay, and so if we now recall that Z1 here, that was the solution set of a quadratic equation on a linear hyperplane, we now need to look, what is this intersection? How does that look like? And so for this intersection, so this basically means it's now, again, a quadratic equation on a linear hyperplane, and this is also a quadratic equation on a linear hyperplane, but they are a little bit different because we had sort of these first few variables fixed to different things. But for this intersection to be non-empty, I mean, this lies in a hyperplane and this lies in a hyperplane parallel to it, and for that intersection to be non-empty, these hyperplanes should coincide. If they're sort of translated, non-zeroly translated of each other, I have something inside here and something inside here, and I intersect, then it's empty. And if it's empty, then this probability that this is inside it is, of course, 0. So in order for having something non-zero here, so some non-zero probability here and a non-empty intersection here, we need those two sort of hyperplanes that they lie in, because they're parallel to each other, we need them to coincide, and that exactly translates to a certain linear equation for those two. So those two need to satisfy a certain linear equation, which we now don't want to spell out what it is, but that we can analyze because it's a linear problem, and so we know by the Littlewood Offord theorem that it happens with this probability, at least if we have the natural non-degeneracy conditions. So in this proof overview, I'm swiping all non-degeneracy conditions under the rug. So this heuristically here just refers to if we check the non-degeneracy conditions, so that we then can apply the Littlewood Offord theorem, and so then we get that probability for this linear problem here in psi I2 and psi prime I2 corresponding to this being a non-empty, I mean just the hyperplanes being a non-empty intersection. Okay, so that means we have this probability that we care about is at most, like on the previous slide, this to the 1/2, but we also know that this thing that we have here is non-empty only with this probability. And so whenever it's non-empty, then that means it's two quadratic things in the same codimension 1 hyperplane. So we have a codimension 1 hyperplane. In this picture, in this picture, the codimension 1 hyperplane that both of them live in is actually all of R3. So for this picture, you should imagine originally we were in R4, and then we had a codimension 1 hyperplane, which is the R3 that your eyes sort of tell you see here. And so that codimension 1 hyperplane is both a relevant one for this one and for this, but now they're described by different quadratic equations on this codimension 1 hyperplane. And those quadratic equations, their solution sets you now intersect. And that's what this picture shows. So this one is the green solution set on this hyperplane, which corresponds to R3 here. And this one is the blue solution set. And so if you see this picture, you see that, oh, the intersection actually is this given by a quadratic equation on, well, codimension 1 inside this R3, so codimension 2 in where you started. Okay, and that you can also check by a calculation. That's simply, I mean, it's a simple fact that if you take a quadratic variety and you translate it, so the important thing is that the quadratic equations here are just sort of translates of each other, then okay, so so then, well, okay, to be very precise, it's not just translates of each other, the quadratic terms are the same. So the linear terms can also vary, but the quadratic terms are the same. Then you have indeed this property that the intersection sort of gives you a linear equation. And so that simply comes from you take the difference of the two quadratic equations and then you apply the trick from before that gives you a linear equation. And so then you indeed get this geometric property that intersection lies inside a hyperplane. And so that means at every step, basically, the intersection does not get horrendously worse and worse and worse with way more quadratic equations. Indeed, at every step, you get one more linear equation, so the linear subspace gets one more codimension, but you keep at every step just having a single quadratic equation. And that's very important because otherwise this would completely blow up. Okay, so this picture suggests, and in fact you can check this properly, that this intersection is now given by one quadratic equation on a linear codimension 2 subspace. Okay, so at the case step, we then have the solution set of one quadratic equation on a linear codimension k subspace, and we need to bound this probability. And so now it's sort of the same idea as before. So at every step, we bound the probability that the relevant variety is non-empty, right? Because you at every step need to translate. And so you might get a translate depending on sort of your outcomes of the psi I and the psi ik and psi prime ik. But in order for those translates to really coincide to get a non-empty intersection, you now have k linear equations, but that you can still analyze. So that's not just simply the Littlewood Offord theorem, it's a version of it for systems of linear equations, but such a version has been known for a long time, since Halas from 1977, and so that you can then apply and then bound indeed the probability that the relevant sort of translates coincide, and so you get a non-empty intersection. And then if it's non-empty, then you sort of expect the probability to lie on it to be heuristically this, so that you again still can't prove because it's sort of k linear equation on one quadratic equation now, but just reality check, you would then expect this. This condition, this probability, and so now what you can see is if you now ignore the quadratic equation and just look at the k linear equations, then you will get this upper bound instead of that. And so here you see already the loss is less in the sense like, okay, the loss is still 1 over square root n, but you get from all these decoupling steps, you get different powers. So in the final bound that you get for this, the term here, because at every decoupling step you get a half in the exponent, has an exponent of 1 over 2 to the k, and so that loss you incur here So you incur a loss of a 1 over square root n factor, but that now comes with an exponent of 1 over 2 to the k. And so that means if you take k to be roughly log n, then this loss from ignoring this is only n to the minus 1 over 2 to the k plus 1. The k step is k is roughly log n, then that's just a constant factor loss. So the idea is you keep doing this, and after roughly log n steps, you can actually afford to ignore the quadratic equation. And then the loss is okay because you get this exponent on it. Okay, so at a high level, that's the proof strategy. However, as you might be imagining, executing the strategy is actually rather complicated. And that's not so much because of keeping track of all the terms, like, okay, that's it's a bit technical, so it looks ugly, so I didn't want to sort of do out the terms, but sort of following what terms should happen there is actually not the hard part. The hard part is to maintain the non-degeneracy conditions. So at every step, you need to maintain certain robust rank non-degeneracy conditions in order for this linear subspace, in order to get the proper probability bounds for things to lie in for this Littlewood Offord systems version of Halas. To apply that, you need these non-degeneracy conditions. And you also need a non-degeneracy condition for the quadratic equation, and you need to sort of properly formulate the right non-degeneracy conditions and then check at every step that they get preserved with high probability. And all of this is sort of rather technical. It actually does require significant ideas also to sort of be able to keep track of these non-degeneracy conditions. So that requires several new ideas to actually make this work. So in particular, just to highlight one tool, so we introduce a new high-dimensional anti-concentration inequality bounding the probability that the image of a random vector under a linear map falls into a small ball in the Hamming norm. So previously there were such inequalities for L2 norms, but here, because of this type of non-degeneracy condition we actually needed a Hamming norm version for this, and that didn't exist in the literature. And so we introduced this, and that also required some new ideas to get this to work. Okay, so all of this is to say, I hope I roughly gave you a sort of bird's eye view on how the proof roughly works, but in fact, there are technical details which I don't fit into this talk and which you probably don't want to see. But sort of maybe you can just believe me that one can then make these technical details work, and then one gets this. Okay, so here let me briefly finish with some concluding remarks. So here's again this conjecture. So this conjecture was for any fixed degree D polynomial with real coefficients under some reasonable non-degeneracy conditions. So here I again put one of those conditions, but you can put either of the ones we discussed before. And then the question is sort of, if you take psi1 to psi n to be independently random 1 or minus 1, what's the probability for this polynomial to take any particular value z? Then the probability is at most, according to this conjecture, 1 over square root n. And this conjecture is still wide open. We proved it for d equals 2, so that was the content of this work. And for d equals 1, it's known by the Littlewood Offord theorem, but for larger d, it's still wide open. And so, of course, it's natural to ask, where can one somehow adapt our ideas also to the larger degree case? It certainly does not apply in any straightforward sense, so one would, maybe some of the ideas might be useful, but one would certainly also need various new ideas in order to apply such a strategy for this higher degree case. Okay, so let me, in the last 5 minutes, talk about a special case of this. So for this problem, we took an arbitrary polynomial, but let's look at the special case of polynomials of bounded rank. So polynomials which we can write as, where we can write the polynomial p as some other polynomial of q, so that doesn't need to be quadratic anymore. It was just sort of the most natural letter for a polynomial now. So some other polynomial q, which just has r variables, and in this polynomial q, we plug in some linear forms of x1 to xn. So if we have a polynomial which can be obtained by sort of applying some r variable polynomial to some linear forms of x1 to xn, then that corresponds to p having bounded rank. And so the problem on the conjecture of the previous slide you can now study in this particular case. And so now, in this case, it's natural to make the following sort of transformation of the problem. So let's consider the matrix whose rows are given by the coefficients of these linear forms. So that's an r by n matrix. So then if we write sort of x1 to xn in one vector x, then this product A times x is precisely, by the way matrix multiplication is defined, is exactly the vector with these entries. And so that means, sorry, that's a typo. So the probability that this polynomial is 0, let's just sort of for simplicity look at sort of taking the value 0, the probability that this is, or the event that this is 0 is now exactly corresponds to that this vector with those entries lies in the 0 set of this polynomial. So that's now the same as A times x lying in the 0 set of this polynomial. And that you can now express as x1, a1 plus and so on plus xn, an lying in the 0 set of this polynomial where these are the column vectors of the matrix. Okay, so just if you didn't follow this, don't worry. So the rest is some simple linear algebra. We can transform, in this special case, we can transform the problem of when does this become 0 into the problem like when does an expression of this form lie on the 0 locus of this polynomial. Okay, and so there was a conjecture about this. So that conjecture is due to Fox, Kwan, and Spink, sort of published in 2023 but formulated a few years prior. So they proved that if we have a polynomial whose 0 locus does not contain any lines, and we have arbitrary non-zero vectors, then if we take these vectors with independent random plus minus 1 coefficients, then the probability that this plus minus 1 linear combination of those vectors lies in the 0 locus should be at most a constant times 1 over square root n. And so for r equals 1, this is exactly the Littlewood Offord theorem. And for r equals 2, this is a special case of our result on the quadratic Littlewood Offord theorem, namely the case of quadratic polynomials of bounded rank. So this exactly in the previous discussion corresponds to the bounded rank case. Okay, and so this conjecture was very recently proved by Grebennikov and Kwan. But I lied to you a little bit. The original conjecture of Fox, Kwan, and Spink was actually not just that. It was in fact more general. So in fact, what their original conjecture is in fact still open. It's the following. It's if you have a subset of RR, which is definable with respect to an O-minimal structure and does not contain any line segment, and then again, you have arbitrary non-zero vectors, then if you take random plus minus 1 coefficients, the conjecture says that the probability that this lies in the set S, in this given set, the definable with respect to an O-minimal structure should be, again, at most on the order of a constant over square root n. And so here, just coming maybe back to your question before, the implicit constant factor in the O notation is allowed to depend on the fixed set S. And maybe also let me briefly comment that this assumption that the set doesn't contain a line segment is necessary here, because if you have a line segment, you could take A1, some point in the interior of the line segment, say the midpoint if that's not 0, but otherwise any point in the interior, and then A2 to AN, you can take very small vectors parallel to the line segment, and then this thing lies in the line segment as soon as psi1 is 1, and that happens with probability 1/2. So in this sort of conjecture, it is indeed necessary to make an assumption of that type. Okay, so that's the conjecture. It's still open, and now I'm out of time, and that's it.